I think tonight's lecture is gonna be a lot of fun. I've been looking forward to this one. So Zen, are you ready to learn about colors? How about some shapes? Tonight, I'm gonna talk about colors and lots of shapes. So let's hop into things a little bit. So we're gonna start off by asking, what is a color? Well, we have a bunch of colors, right? Like red and green and blue. And you notice that I'm using this weird hexadecimal notation. So a system where we have the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14, 15. So if we have two of these numbers ranging from 0 to 15 next to each other, they give us a number between 00 and 255. So when we write FF0000, we're saying that there's 255 red, 0 green, and 0 blue. We can nudge that around and say that there's like a bit of red, no green, and then some blue. And we get kind of a pinkish color. And we can add some more blue to nudge it more towards purple. So what can we observe from this? There are three main things that we mix to get most of our colors in light. Redness, greenness, blueness, and then there's one other that we call alpha, which is like an opacity / transparency. We could have lots of this color, but then like we make it very weak, so there's none of it showing. Or maybe we make it very strong, so it's all showing. Or maybe we make it kind of in the middle. So something like 6/6. So you see that it's starting to blend in more with the background color. So I care about how red, how green, how blue, and how transparent or opaque. Alpha of 0 means it's completely invisible, and alpha of FF means it's completely visible. So now let's go and shift our focus a little bit. And we're going to talk about ppm image. So we're going to make a little image here called test.ppm. I'm going to talk about the ppm image format because it's human readable. So we can actually write down a ppm image. And let's do a quick example of that. So it starts with a little bit of information about formatting. There's format 1, so P1, format 2, and format 3. Format 1 just says we can do 0 or 1 to turn on and off things in a pixel grid. And we're going to talk about what a pixel grid is in a second. Format 2 lets us have grayscale. So we have one color, black and white, 0 to 255, representing black to white. 3 gives us a red, a green, and a blue. So we're going to use 3 so we can have color. And then on the next line, we're going to specify how many things there are. So how big our image is. First thing is width. For this example, we're going to say 2, and then height, which we're also going to say is 2. Then we need to mention, what is the scale of this image? Is this 0 to 255, 0 to 6,000? What's our scale? So we're going to say that it's 0 to 255. Now we're going to need a couple of colors. So let's do red, which is 255, 0, 0. We're going to do green, 0, 255, 255, 0. We're going to do green, 0, 255, 0. And we're going to do blue, 0, 0, 255. Earlier, when we were doing the hexes, right, I had to be using FF in place of 255. But in the ppm image, it wants the number 255 spelled out. And then we mentioned that this was a 2x2 image, so it's expecting 4 pixels. We've only specified 3. Let's do white, which is all red, all green, and all blue. Let's give that a save, and we should be able to open that image in an image editor and see our red, green, blue, and white pixels. So the first bit of code we're going to write tonight is a small library to help us write these images. When teaching about ppm, because it's a lot easier to spit out a ppm file than it is to try and hook up creating a texture with software and then like putting it in a window. So we're going to be doing offline rendering when we want to run our program and we get an output. It's not quite what we want. We wouldn't want to make a game that way. But for the purposes of learning how to render an image, works perfectly fine. So we're going to make a little library here, which we're going to call ppm.c++ header. And the first thing we're going to do is we're going to make a struct called color. And we mentioned that a color is 0 to 255, and C++ gives us a type that fits that size perfectly. uint a_t, which happens to be able to store any number from 0 to 255. We have 3, red, green, blue, and to access uint a_t, we need to include the C standard int library. Cool. So we now know what a color is, but what are we going to do for actually writing out the file? So I'm going to make an inline std ostream reference write ppm. So an ostream is C++'s method of writing content to a file. Technically, it's writing it to anything. Like cout that we've used is an ostream. And so you'll see that a lot of the output things that we're used to using will look very familiar. Well, what won't look quite familiar is that we're going to take an ostream reference out as input. So we're going to start off by writing our header. So we're going to go out p3 for format 3, and then we're going to go a width and a space and a height. So since we're specifying width and height here, we need to take those in. So we're just going to say that there's an integer width and an integer height that we can take as input. And then we need a new line. And now we're going to specify 255, and that will be the main thrust of our header. So now we need data. So it's time to talk about how we're going to organize this data. This function expects the data to be written. If we look at the order, right, the red pixel that we specified first shows up here. Then the green pixel we specified second shows up here. So it's expecting the data in row order. So we're going to get this many bits of data. So this many are columns, bits of data. Then we're going to move down to the next row. So we're going to need to remember that. But for right now, we're not going to care. We're just going to say that we get a blank view. So std span of colors. And this is going to be our color data. So we're going to need to include span. Since we're using span, we're going to have to go cmake lists.x and set cmake minimum required version 3.21 project software rasterizer C++. And then we're going to go add executable render. And then we're going to take render.cpp. And then we're going to go set target properties, render properties, XX standard 20, so that we have access to span, and it wants version to be in all uppercase. Cool. So if we now include our little header, so include ppm.hpp, we should see that it doesn't care about span anymore. It should be happy to let us use span. So how are we going to spit out the data? Well, we're going to loop over every bit of color in our color data, and we're going to output the red, so c.red, and then a space, and then c.green, and then a space, and then c.blue, and then a new line. So this will give us all of our color data with 1 pixel on each line. The last thing, just for completeness' sake, is we're going to return out with a call to std flush. And this will just make sure that everything we wrote here gets printed out to the file. Let's go over to our render, and we're going to make our int main. And we're going to try and emulate our test image here. So we're going to make a std array of color. We're going to make 4 of them, colors. And we're going to go colors 0 equals red, so 255, 0, 0. Colors 1 equals green, so 0, 255, 0. Colors 2 equals blue, so 0, 0, 255. And then colors 3 equals white, so 255, 255, 250. Now, if we use our write ppm, we need another bit of information. We need a std of stream, output file stream, which we're going to call fout, and we're going to open result.ppm. So you notice it included the fstream library for us, and an fstream works almost like cout, so we can go fout hello world if we so wanted, but instead of writing to the console, it's going to write to this new file that we're going to create. So we're going to tell it to do all of the writing to this file. We're going to say that we have 2 and a 2x2 image, and that our color data is colors. Now, if we run this, hopefully, we should get in our build folder a result.ppm file, which if we open it, so there is a little bug here. The data that we wrote out it's trying to do binary encoding of the characters, and that's not really working. So we'll just tell it to print out the characters as the integer form. So we'll run it again, and we should have pretty much the same image that we had last time with the red, green, blue, and white. We can change this a little bit. As long as our width times our height adds up to 4, we can put whatever we want here. So we could say that it's 1 wide and 4 high. We run it, and we reopen our image. We now have a vertical stripe with all of our pixels. We do the other way, 4 wide and 1 high. We rerun it, we'll see that we have a horizontal stripe with all of our pixels. However, if we put something that doesn't multiply to 4, so like 5, 1, we'll run this, and when we open it, we should get a parsing error saying, hey, I was expecting 5 things and I only got 4. So let's add a validation for that to our header real fast. So up at the top, before we do anything else, let's assert that width times height is equal to color data.size. So an assert comes in the CAssert library, and we're just saying that this thing is true, and if this thing proves not to be true, I'd like you to crash the program. So for 1, the program should run fine, but 5.1, the assert should fail, and it will complain about the width times height is not equal to the color data.size. And it should even tell us what line the issue came from, which is cool. So let's now start thinking about how we can organize this color data. So right now it's a flat array, but we don't tend to think about images as being a flat array, right? We tend to think about them as being two-dimensional. So let's make our array two-dimensional. So instead of having an array 4, let's have an array 2 of array 2s of colors. So something needs to change here. We now need to start specifying a two-dimensional axis. But let's think about how this color data is stored. So our image is expecting a value for each column, and then those columns sorted into rows. So this inner array is representing the data for each column. So we're going to have column, 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 and then this outer array is going to be storing data for our rows. So this will work. We just have to be aware that accessing into these is going to be backwards. So we're going to go column 0, row 0, column 1, row 0, column 0, row 1, column 1, row 1. And this should, if we pass colors.data, we're going to have to do a little bit of tweaking here. We're going to have to go a color pointer, colors.data, and now we need to specify colors 0.size times colors.size. So manually convert our data into the linear stream. It should already be stored in memory the way we want it to. We just need to get C++'s type system, bypass it a little bit so that it becomes correct. And we should have a very similar image. Let's create a big image. So 255 by 255, and let's fill it with some like raw data. So we'll just make it blank. So to start with that, we're going to go for each of our columns. So for size t, y equals 0, y is less than colors.size, colors 0.size. So we want the size of this inner array plus y, and then for size t, x equals 0, x is less than colors.size plus x, and then we're just going to set colors, our y, and then our x equal to some color. I pick 0, 25, 200, which should be a nice bluish color. If we run this, we need to specify that our image is 255 by 255, or to make things even easier, colors 0.size, colors.size. So it'll update automatically if we resize it. And this should now just be a blank blue image. So that's not particularly exciting. So let's pick some point, and we're going to color it in. So we'll set colors 25, 25, and we'll set it equal to 255, 178, 77. So let's look at what this is. This should be all red, half green, and a little bit of blue. A little bit more. 128, so 255 over 2 is about 128. So 128 is half of something. This is a little bit more than half green, and this is about a third bluish. So when we take mostly red, a bit more than half green, and a little bit of blue, we should get a nice orangish color. And if we render out our image and open it up, we should in fact see that there is a single orange pixel hiding away in our data. So one orange pixel isn't particularly exciting. Let's make a bigger point. So let's start by drawing a rectangle instead of just one point. We are going to save this because I want this color very easily copyable. So we're going to define a size t width, which we're going to set it equal to 3, and a size t height, which we're going to set equal to 5. So we're going to draw a rectangle that's 3 pixels wide and 5 pixels tall. So how are we going to do that? Well, we're going to go for size underscore t, y is equal to, we have to pick some starting point now too. So we're going to go with 25, 25. So 25 minus width, and then y is less than 25 plus y. Or size underscore tx equals 25 minus height. X is less than 25 plus x. And now for every value in this pair, we're going to set its coordinates, its color, to be orange. And we should see when we run this that we get a little rectangle. And this little rectangle should be 3 pixels wide and 5 pixels tall. So this in and of itself, the weirdness here was because I was doing height on y and width on x. So when we correct that little blunder and we look at our image, we should see that we have a nice little 3 pixel wide rectangle and a 5 pixel tall rectangle. So this gets into now talking about the 3 main types of drawing that a GPU will do for us. A GPU will draw us a point, a line, or a triangle. So if these are the 3 things that the GPU can draw, why did I start off by drawing a rectangle? Well, because we're going to use this rectangle drawing technology to implement a lot of these other types of drawings. So what do I mean? Well, let's implement a point real fast. So a point will have a radius. So we're going to say radius equals 3. And now we're going to do something very similar. So we're going to say that we have a point with its x is equal to 25 and its y is also equal to 25. So we're going to go for, and we'll put little underscores on the end of these. Size underscore tx equals x underscore minus radius. X is less than x underscore plus radius plus x. And we're going to do the same thing for y. For size underscore ty equals y underscore minus radius. Y is less than y underscore plus radius and plus y. And now let's just fill in that whole bit with our color. Turn off our rectangle so that we don't get any conflicting messages and give this a render. And we should see that there is a 6 by 6 point centered at around 25, 25. But that's not super point-like. It's just a square, right? So how can we go about and constraining this square to be more of a point? Well, we can check if any point is within a circle by checking if its distance from the center of the circle is greater than the radius. Hey, look, we happen to have some of that information. Well, how do we calculate the distance from a point? Well, we can do some vector math. We want the line. We want line from point to circle center. So what is our point? Our point is x and y. And what is our circle center? X underscore and y underscore. So we want the line from the circle to the point. Doesn't really matter which way it is because the main thing we care about is the distance. So let's get that line. Well, that would be a size underscore t. Change in x is equal to x minus x underscore size underscore t dy. Change in y is equal to y minus y underscore. And this now tells us the coordinates of the line from the point that we're currently rendering to the center of the circle. But we want to know how far away that is and how that compares to our radius. So we just need to get the length of this line. That, if we recall, length of a line is the square root of x times x squared plus y times y squared plus what, etc. Z squared, w squared, and so on. So we can find the square root of dx squared plus dy squared, but we can do something a little bit cleverer. Instead, if we have r is equal to the square root of x times x plus y times y. If we simply square both sides, we're going to have r squared, so r times r is equal to x times x plus y times y. So we square this side, get rid of the square root since square root and square undo each other, and then r squared is simple r times r. So what we can check is if dx times dx plus dy times dy is less than radius times radius. And if that is the case, then we can color in our orange. You'll notice that when we render this, not a whole lot should have changed. Our circle got a little bit smaller, but it's still pretty square. That's because this is not a very accurate calculation. We're throwing away a lot of details of the length by just snapping everything to integer coordinates. But we will see that if we make the radius bigger, so something like 10, and we render it, we're going to get a lot more of something that looks like a circle. And the bigger that our circle gets, so we'll go 25, so it should now bump up against the top of the image. The bigger our circle gets, the more it will start to look like a circle. So this idea of drawing a rectangle and then carving out some parts of it we don't want is very powerful. So say we wanted to just draw a rimmed circle, so just the outline of a circle, we could do it again, right? So we could go, if the length is greater than, say, the radius minus 3 times the radius minus 3. So now we're checking if it's inside of this circle with a radius and outside of this circle with it's a little bit smaller. And that should give us just the outline of a circle. Turns out, just carving out parts of rectangles is very powerful. We can draw almost anything that way. But there is a downside. Let's continue on this. The loop moves on. And so if we don't actually draw the orange, we're going to draw green instead. 0, 2, 55, 0. So what we're going to do here is if this check passes, we're going to color it orange. But if it fails, we're going to color it green. So the idea is everything that we want to draw is going to be orange, but everything we had to consider to draw that orange, we're going to highlight in green. And if we look at this image, you'll see that we have to consider the whole rectangle, even though we only want to draw something in this tiny bit of it. So using this rectangle idea is very powerful, but also a little expensive. So we spend a lot of time trying to come up with ways to minimize the amount of green that's being drawn here, which is something you'll see when we start talking about lines. So how can we draw a line? Well, there's the famous equation for a line. Y is equal to x times slope plus intercept. We're going to do a very simple line that's going to go through the origin, so our intercept is 0, and it's just going to go down 1 pixel at a time, so its slope will be 1. So what we can do is we can just straight up draw a rectangle and then check if these conditions are true. So we're going to create a couple of variables for where we want our line to start and stop. So we're going to make a size underscore t top x equals 10 and a top y equals 10. And another one, size underscore t bottom x equals 10, bottom y equals 20. We want 20 here. And so we're going to start drawing our rectangle. For size underscore ty equals top y, and then y is less than bottom y plus y, or size underscore ty x equals top x, y is less than bottom x plus x. So if we just color this in, we'll get a rectangle around between these 2 points. But instead, we want a line. So we got to do a little bit of calculation. We have to go and calculate the slope of this line. So we're going to go size underscore t dx. The slope is equal to bottom x minus top x, which for us is going to be 1. Size underscore t dy equals bottom y. Sorry, is going to be 10 minus top y, which for us is again going to be 10. And then we want to solve that line equation. So if we move the y across, you'll see that we can rewrite this as 0 is equal to x minus 1. We have our slope here, right? So this is dy over dx. And then this intercept can be calculated, but we know that for this line, it goes to 0. So x times dy over dx plus 0. So we'll put that in, and we're going to check if x times dx over dy plus y is equal to 0. And if it is, color it in with our nice orange color, and we'll hide our points, and we will pray that it does not once again blow up at me, which it kind of appears to be. We have an X there. Yang. Well, what we can do, we can say if our dy times x minus dx times y plus dx times b equals 0. And we know here that our b is equal to 0. Just the point where we intercept the y-axis. Then when we run this, if that's equal to 0, we should be able to see our line. People smarter than me have been able to derive what this formula, and with any luck, we have a nice little orange line. But there is a problem. So let's do the else condition, and we'll print out everything we consider to draw this line. So colors, y, x equals green. And when we render that out, we will see that we have to consider the whole rectangle around the line to draw just this little line. So we're drawing just a little sliver of this, but we're wasting all of this space. Well, it turns out that some really smart guy named Bresenham created a nice line algorithm where we're able to just go horizontally across the image. So to start things off, we're going to need a lot of the same fields. So we're going to need our points as well as our differences. And we calculated it like normal for the previous simpler line algorithm. But now we also need two more things. We need a value d, which is equal to 2 times dy minus dx. And we need a value y, which is going to be equal to top y. So we're going to set y outside the loop. Now we're going to go for size underscore tx equals top x. X is less than top bottom x plus x. So we're just going to loop across this one axis, and we're going to immediately set the color to our orange. Then we're going to go if d is greater than 0, y equals y plus 1, and d equals d minus 2 times dx. So the idea here, if we finish this off, d equals d plus 2 times dy, is that we are checking every step. Are we closer to the line? So is the pixel on the same line closer to the line, or is going down 1 pixel closer? So if we keep track of all of this in this little d variable, and as soon as d becomes positive, it means that we'll become closer if we go down 1 more. So if it's closer, we subtract off how much we need to move along the x. And then each time we add on how much we need to move along the y. And as soon as it becomes closer to the line to move down a pixel, we subtract off the x and continue. If we run this, we should see that we get a very similar line to the previous one. But if we also in here colors top y, x colors and set that equal to green, we can see that we have to consider so much less. We only consider a line, 1 pixel for every pixel we draw, instead of the whole rectangle in the naive line drawing case. Unfortunately, the algorithm that uses Bresenham lines to draw a triangle is not particularly good. It's called the scanline algorithm, and we're going to mention that in passing, and then we're going to immediately move on and start talking about the actual algorithm that everybody uses. So to start drawing a triangle, we first have to talk about the area of a triangle. So have to talk about the area of a triangle. So triangles have a very famous area formula. A equals 1/2 of B times H, base times height. Well, it turns out for our purposes, that's not a very useful algorithm, as we have 3 points. So something like 100, 50, 150, 150, and 50, 150. Well, how do we figure out what the base and the height of these are? It's not entirely obvious. So there's another much less well-known algorithm to figure out the area of these triangles. And that formula is area is equal to the absolute value, very fun, of, and we're going to call these points A, B, and C. So the area is equal to the absolute value of B dot X minus A dot X times C dot Y minus A dot Y, that minus B dot Y minus A dot Y times C dot X minus A dot X. And then we take all of that and we divide it by 2. So depending on which way around the triangle is. So if we have a point here, let's do an orangey color. Here, 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 where we draw the points in a clockwise manner, this will give us a positive area. But if we do it the other way, right? So we draw a point here, here, then here. So in a counterclockwise manner, it will still give us a positive area because of this absolute value. But if we get rid of that absolute value, we'll get a signed area, and it turns out that when we draw things clockwise, our signed area is positive, so positive for clockwise. But when we draw things counterclockwise, the signed area is negative. Well, if we define one of these as being the front of a triangle, so clockwise or counterclockwise, then we can immediately apply a very quick optimization of not rendering any of the back faces, which is called backface calling, just by checking the assigned area. Also, if we then get rid of that division by 2, we get what's called an edge function. So the edge function is this function, but we get rid of that division by 2. And it is interpreted a little bit differently. Instead of a C here, we have a P. And what this represents is if we have a point A and a point B, and we draw a line between them, where is this extra point? If the value of the edge function is positive, it's on the right. Right is defined, we're standing at A, looking at B, and if C, our point that we're considering is on the right, it will be positive. But if the point is on the left, it will be negative. Why do I mention standing at A and looking at B? Well, because if we're standing at A and looking at B, then if this is forward, right, and C is over here, that's still positive. Because from the perspective of A, it's on the right, even though it's on the left for us. So the thinking about the perspective of A towards B is important here. Well, how is knowing whether a point is on the left or right helpful? Well, let's look at a triangle. So we have our line, we have another line, and then we have another line. And we're going to tip them, so give them directions, flowing from A to B to C. Well, and what do we notice? We notice that if a point is to be inside of the triangle, then it's on the right of the line from A to B. If it's inside the triangle, it's on the right of the line from B to C, and it's on the right of the line from C to A. So if any of the lines do not pass this is the point on the right check, assuming that our triangle is round clockwise, then we know that point's inside. If the triangle is round counterclockwise, we have to check the opposite. We have to check if it's on the left side. So we can do something very similar to what we've done before. We can draw a bounding box. Let's do that in red. We can draw a bounding box around our triangle, draw all the pixels there, and for each pixel, we check, is it on the right of every line? And if the answer to all 3 of those is yes, then we can assume that that pixel is in the triangle. And if the answer is no, then we assume that it's outside of the triangle. So let's implement it real fast. So we're going to do it in steps. The first step is we're going to come up here and we're going to implement a struct vec2, which has a point x and y. We'll need to implement our edge function that we just talked about. So we create the vector 2 so that implementing these 3 points becomes a lot easier. So let's create a float edge function, which takes the points back to A, back to B, and back to P. So now we should be able to return B dot x minus A dot x, assuming capitalization is correct, multiplied by P dot x, P dot y minus A dot y plus B dot y minus A dot y times P dot x minus A dot x. And now let's go down and we're going to find what's called a bounding box for our points. So we're going to start off by actually implementing our points. So back to A, back to B, back to C, and now let's find the bounds of all of these points. Well, what we care about is the minimum and the maximum along each axis. So we're going to find size t min x, which is going to be equal to stood min size t, and we can pass in brackets a list of several things, more than two. So A dot x, B dot x, C dot x. And in order to get stood min, we need to include algorithm. And this will give us the minimum point along the x. So we're going to do something very similar, but for max x. Now we're going to do something very similar, but to find the min and the max y's. So y and y. This now tells us what the bounding box of our rectangle is. How's that useful? Well, we can start by drawing a rectangle that is this bounding box. So we're going to go for size underscore t y equals min y. Y is less than max y plus y, or size underscore t x equals min x. X is less than max x plus x. And we're going to just do a rectangle, so we're going to add our coloring. And we're going to turn off our line rendering. So if we render this, we should see, I will discard, that we have a big scary box, but no triangle yet. So we discussed that the way we figure out if a point's inside the triangle is by asking, is it on the right side of each of the edges? So let's do that check real fast. So we're going to start by defining a vector 2, p, which is going to be equal to x and y. Now we're going to say float right AB is going to be equal to our edge function, A, B, P. And so this should be positive when P is on the right side of AB and negative otherwise. Now we're going to do BC, so BC, and we're going to finish the triangle going back to A. So we're going to do CA and CA. Now, if we check if right AB is greater than or equal to 0, and right BC is greater than or equal to 0, and right DA is greater than or equal to 0, and I didn't make any mistakes. When we color it in only those conditions, we should now have rendered, sad, what did we mess up? Oh, it would be because I did not set these to be floats. That's why everything's on fire. Yang! I need more accuracy. That makes sense. It's almost like the precision issues might be causing me grief. Or something like that. Oh, hey, look. It's almost like the precision issues might be causing me grief. Worked and scuffed? Turns out using the correct type of data might be important for this problem. But anyway, back on track with our float modification done here real fast. We will see that we have our nice little triangle drawn. So we've checked that all the points outside happen to be on the left of one of the lines, and all the points inside are on the right of all of the lines. Well, it turns out that doing it this way, even though it wastes all of this extra, let's visualize how much we're wasting, even though it wastes all of this stuff that we're going to draw in green, get rid of you, open you, and we notice that the amount wasted is not insubstantial, right? It's a whole nother triangle's worth. So even though we're wasting a whole nother triangle's worth of pixels, what we're able to do is interpolate values across the triangles very effectively and pretty easily. Well, how can we do that? Well, if we take these values and we start off with another very simple value, so we're going to do something simpler, and we're going to go ABC. Instead of comparing against a point, we're going to compare against C. Now we can create weights. So float weight C equals right AB over ABC. Float weight B equals CA. And float weight A equals BC. So what we're doing is we're taking the edge function value of the whole triangle. So this is roughly equivalent to double the area. And just like these are double the area, right? If we divide by the double the area of the whole triangle, well, the doubles cancel out. And so these just become area divisions. And so these determine how much of the triangle is taken up by this side. So the downside of the rationale here is that if we have point A, B, and C, to figure out the weight of point A, we want to figure out the line here, right? So we're taking this line and we're finding the area relative to A. Well, doing that, right, gets us the weight of A. And if we quickly scan through these, right, you notice that we're doing the weight of C relative to AB, the weight of B, right, relative to the line that doesn't include B, the weight of A relative to the line that doesn't include A. And then we're going to skip ahead a few iterations. Actually gonna skip on this. A few iterations, get a Y at around 100, and then we'll get an X at around 100, and that should be firmly in the middle of the triangle. So we should get positive numbers, all of these, yep. And since this should be near the middle-ish of the triangle, the weights should be kind of similar. I guessed wrong. We're closer to the top. So we picked a point at 100, 100, which I think is about here. So A is closer, right? So A has a slightly stronger weight, and then C and B are about the same. Fun fact about these weights, if we add them up, so float little weight, and let's not do it here, we'll do weight CA plus weight B plus weight C, they should always add up to 1. So if we multiply something by these weights, view them as percentages, right? Once they're all added up, they should equal to 100%. So let's do this, the simplest thing. We're going to take a color and create a color for each point. So color A, and we're going to set A to red. Color B, and we're going to set B to green. Color C, and we're going to set C to blue. And now, instead of printing out our color, let's compute a new color as a combination of these weights. So we're going to go float R equals weight A times color A plus color A dot R plus weight B times color B dot R plus weight C times color C dot R. And it really is that simple, right? We can just take all the colors, multiply them by the weight, and then repeat the process for G or B, and then output colors YXY equals RGB, but it will complain because we want these to be UNATs, just like our color output. So if we now run this, we should get a very beautiful triangle that interpolates nicely from red to green to blue. You notice how richly the colors blend into the browns in the middle here? If you do a version where you draw this line, let's do that in black. We draw this line, and then this line, and then this line. We can do another algorithm where we then take boop, 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 and draw all the lines going across. That will wind up not considering this extra wasted space. So this stuff in yellow won't get considered anymore. But the way all the colors blend and interact with each other becomes a little bit worse. So I'm teaching the algorithm that blends things across the surface of the triangle nicer, as opposed to the algorithm that minimizes wasted pixels. It turns out that we still wind up even having to consider all of these pixels, so it only really winds up saving the yellow pixels. I mean, that's still consideration, but I lean towards nicer blending. And although the GPU manufacturers don't publish the algorithms they use to do their triangle rasterization, based on how their blending works, it's something more similar to what I'm presenting today than something else. Although what they do is a little bit more hierarchical. So they take our image and they split it up. So they go image. Now we're going to split it into quarters. There's stuff in this quarter, there's stuff in this quarter, there's stuff in this quarter, there's stuff in this quarter. So we consider all the quarters again. Then we're going to take this image, split it into quarters. Well, we can just immediately throw out everything here. Split this one into quarters. And we can immediately throw out everything here and here. Split this into quarters. And they continue like that, splitting more and more parts down into quarters, being able to throw out more and more until they get down to the scale of 2 pixels. And then they just render those 2 pixels. Turns out that they render the 2 pixels so they're able to compute differences in values between the pixels. So there's a function that GLSL gives you called dx and dy, which tells you how much a value that got inputted from the rasterizer changes between up for dy and right for dx in the fragment shader. I believe that was everything I planned on talking about tonight. We've been able to create a system that outputs images for us that we can open in an image editor. We've been able to create a system that renders, let's go through them all, turn off our triangle, that renders points, or circles in this case, since we're doing a little bit more computation to cut out a bit. A system that's able to render lines. Look at that beautiful little line. And, of course, a system that is able to render triangles. And then, as a reminder, this process of taking, say, a triangle and converting it into pixels that we draw is called rasterization. So when I talk about the rasterization step of the GPU pipeline, here's the code that does something similar. It's not particularly complicated. The way a GPU actually works will be a little bit more complicated, because instead of doing this for loop, they run everything at the same time. Remember, a GPU has a couple thousand cores that can do small amounts of work. So they take each of those cores, assign them to one of these, and then run all of this at the same time. That's how they're able to make things go so fast. It takes quite a while for us to rasterize a triangle in software, but since the GPU is doing all of it at approximately the same time, it's much faster for them.